Okay, the button's been hit. A good way to start a recording. So, we're in chapter 14. Yes, I just recorded you asking me if I recorded like that. So, let's consider that to be our introduction to chapter 14, number 51. Now, we're given this reaction that's not very exciting, that A becomes B. And we're given the K value of 4. Now it says, find the equilibrium concentrations of A and B for each value of A and B, lowercase. So we're saying, what if the coefficients are different? Assume that the initial concentration of A in each case is 1 molar and that no B is present. All right, so we're going to do a little chart here. The first thing we need to do is write the expression for K. So how do we write that here? Okay, so that means this is to the beef. I think that's a technical term. And this is A to the 8th. I think this is A, 8. All right, that's ugly. I don't like that D.
Yeah, the style is,
Hey. Now, what I'm going to do is this little chart for to help me think about the concentration of A and the concentration of B. And so I'm going to say initially, what is my initial concentration of A? 1 molar. What's my initial concentration of B? 0. Now, those are my initials. Then I'm going to think about the change. What's going to be my change in A? Okay, we know it's going to be something negative because we're going to lose it. But we don't know how much we're going to lose, do we?
Are we going to equilibrium?
We're going to equilibrium, but we don't know how much we're going to lose to get to equilibrium.
Negative A.
So let's just call it X for algebra. All right? So then what I'll do is think about what my B will be. Yeah, it'll be positive X in this case. Because if I lose X amount of A, I'm going to get X amount of B out of it. Okay? Now, to finish off my little ice chart here.
You're icy.
The concentration of A is going to end at what? 1 minus X. And then the concentration of B at equilibrium is going to be X. Okay? Now, for, we're looking at A right here. So, for A, it says that my coefficient is 1 and 1. All right? Which means that for this, I'm just looking at B over A. Now, what that means is I can plug in my numbers. So if I do K is 4, the concentration of B is going to be X, and the concentration of A is going to be 1 minus X. Okay, you see what I did there? I just plugged in all the values at equilibrium. Because it said right here, the initial concentration of A is 1. And then it said here, for part A, assume that the little a is 1 and the little b is 1. When we get to part B, we're going to do 2 and 2. Okay? So now I just have to solve for X. Which, solving for X isn't so bad, right? We all took algebra, we all passed algebra. Got an A in algebra. So, we'll just multiply both sides. We get, 4 minus 4x equals x. And then we'll add the 4x's over there. So 4 equals 5x. 4/5. Well, right? right? I mean, it's algebra for there.
Oh, decimals are better?
Whatever. It's just confusing when I wrote it.
Oh, 0.8. I can't see that dot.
Is that 0.8?
No, didn't like when I did that. 0.8. Okay. Now, if x equals 0.8, we want to know what's the concentration of A going to be and what the concentration of B is going to be. So the concentration of A is going to be what at equilibrium?
0.2.
0.2. You guys see that? 1 minus 0.8 because x is 0.8. So the concentration of A at equilibrium is 0.2 molar. And the concentration of B at equilibrium? What's the concentration of B at equilibrium? Yeah, it's just 0.8 because it says right here it's just x. Okay, does that make sense? All right, now let's do B. So, let's see, I think I can... Will it erase my picture? It will. I don't want to do that. Also erase it the old-fashioned way. Erase all this. It's like erasing my chalkboard. Isn't the future fun? You know what? I'm going to leave that stuff there too. Because I can. That's why I'm leaving it. Now, here, it says that for B, little a equals 2 and little b equals 2. So how does that change my k expression? Okay. So now, in B, I saw the same initial conditions. What's my change going to be for A? What goes right here? Is it going to be positive or negative?
Positive? No, wait.
No, negative because you lose it.
Yeah, and this time it's going to be 2x. Because every time I do this reaction, I lose 2 A's. And that means I'm going to get what out of B? And for every negative 2x I change A, I'll change B by positive 2x. And then what's going to happen at equilibrium? What's my equilibrium at A?
1 minus 2x.
1 minus 2x. And then for B?
It's just 2x.
Just 2x. Now, what's my next step here?
Put in the...
Okay, so 4 equals 2x squared over 1 minus 2x squared.
Can you just square root all of it?
Yes, we can. Okay, so you're looking at it and you're thinking that algebra looks rough, doesn't it? The good news is we can take the square root of both sides. So we can take the square root of that and the square root of that, which is just going to leave me with 2 equals 2x over 1 minus 2x, which is a lot easier to solve algebraically, isn't it? Yeah, I mean, I just went through the steps in the last one, so I'll just go ahead and tell you that x is going to equal 0.33. You already know how to solve that algebraically, though, right? Because you all got A's in algebra years ago.
Well, where's my question?
Of course.
Years ago.
But
A question?
I got a little bit lost when you did the negative 2x, positive 2x.
You mean right here? Yeah, I'm just saying that I don't know how much I'm going to lose of A, but however many times this reaction happens, x, for x times that this whole reaction goes forward, I'm going to lose 2 A's every time it happens. So x is my variable that I don't know how many times the reaction is going to occur. But I know that every time I do it, I'm going to lose 2 x's. Yes. Come on.
I don't get what's going on the website. Like, where are you, the ICE and where are you getting the numbers?
So this is my initial. And I'm just getting that from up here. The initial concentration of A is 1, and no B is present. So that's where my I is coming from. Okay? Then my C is my change. And that's where I'm saying that between my initial condition and my equilibrium condition, some of my reactants are going to become products. How much? I don't know. But however many times this reaction happens, my change in concentration is going to be negative 2x. 2 from the coefficient, negative because it's a reactant. And then what I'm saying is that if I lose negative 2x worth of reactants, I'm going to get negative 2x worth of products. And then all I'm doing is for my equilibrium, I'm saying if I started with 1 and I change by minus 2x, that my equilibrium concentration will be 1 molar minus 2x, where x is however many times I did the reaction.
So do you always set that out for those kind of problems?
Yes, I'm going to. Let's set this ice thing. Initial change equilibrium. And then I take my equilibrium, the equilibrium part. The whole reason I do it is to find the equilibrium stuff to plug in to this equation. All right, so now that I got x equals 0.33, that means that at equilibrium, what's my concentration of A going to be? So it's going to be 1 minus 2 times 0.33. So it is 0.33, isn't it? And the concentration of B is going to be 0.66. Okay, and those are those are molar. Those are my concentrations. All right, now let's do C. So
What is the concentration of these things?
0.66 molar, because it's just 2x. Now, in C, I have, oh, that's terrible, a coefficient of 1 there and a coefficient of 2 there. So, let's go back to the drawing board. Now, how does that change my equilibrium expression? Because now B is going to be to what power? And A is going to be to what power? Yeah. To the power. All right. So let's work it one more time. So what's the change in concentration of A going to be? Negative x. Yeah, just negative x. What's the change in B going to be to move towards equilibrium? 2x. Because look at my ratio. It's a 1 to 2 ratio now. That means that my equilibrium value for A is going to be 1 minus x. And for B, 2x. Okay? Now that I know that, I'm going to do what? So I know that I still have that same value of 4 right here that they told me. And I'm going to plug in for B 2x squared divided by 1 minus x. Okay, now I need to solve that. So I guess I'll go ahead and multiply both sides by 1 minus x. So I get 4 minus 4x. I'm just doing algebra now. Equals, well, 2x squared is 4x squared. Okay. And I got x's all over the place, so I might as well get everything on one side of the equation, right? So I guess let me put my 4 minus 4x back over there. So I'll take my 4x squared, I wrote that pretty big. My 4x squared, I'm going to add 4x to both sides, and then subtract 4, and that equals 0. Now, what do you see? Mm-hmm.
Just factor in the 4 and then.
Mm-hmm. Ultimately, here's what I'm alluding to. Do you remember your old friend, this guy?
I always sing the song in my head.
Yeah, he still exists. You remember how to use the quadratic formula? What's all this BAC stuff?
Well, if you label 4x squared A, 4x B, negative 4c.
Standard form.
Yeah.
But in this case, they're all 4.
So, I'm going to assume that you guys can do a quadratic equation. Now, here's the thing. Whenever you do the quadratic equation, you're going to get x equals negative 1.6 or x equals 0.62. Because remember, our quadratic equation always gives you two solutions. Well, I only have one equilibrium. How can I have two solutions in one equilibrium?
One of them is one's A and one's B.
Which one? So which one do I? What do I do? Which one do I pick?
Well, you
Can't be negative. One of these answers is imaginary and one of them is real. Which world do we live in? The real one.
Not really the world.
So we just kind of goodbye imaginary answer. That actually happens a lot in chemistry and physics. We come up with a lot of imaginary answers. We go, oh, it must be the real one then. That's the world we live in. We can't get an imaginary circumstance that actually happens. So now I know that x equals 0.62. That means that my concentration of A at equilibrium equals 0.38. That's 1 minus 0.62. And the concentration of B,
1.24.
yeah, it's going to be 2x, 1.24.
It can be greater than 1 and added together.
Sure.
Oh.
Because look, I'm going from 1 mole to 2 moles.
Right.
And that's my solution. Now, if we weren't sure that we did this correctly, because we had quadratic formula stuff, we were moving things around, there's lots of numbers, it's a mess. It'd be easy to make a mistake, wouldn't it? One little thing. It's easy to check yourself. All you have to do is go up here and be like, well, if I put in 1.24 squared over 0.62, I know what that should equal, don't I? Better equal 4.
Yep.
Spoiler alert, it equals 4. It does. This is 4. Okay. That's how we know we got it right. Because my equilibrium concentrations do come out to my equilibrium constant. Yeah, that's just checking it to make sure when you do all this algebra and quadratic equation stuff, it's easy to miss something and you lose confidence in your answer. That's how you regain your confidence.